Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
Looking at virtual work for this particular problem, we want to determine the moment as the block compresses the spring. Okay, okay. So this is a block as it compresses the spring. Let's say we have two members here, linkages. Okay, set to the angle theta, and this one too is theta. Angle there is theta. All right. The supports here. All right. So, and there's a moment here, M, as well as here, M. Now, to solve the problem, what we need to do is to determine the virtual work due to the width of the block, as well as the virtual work due to the force, the spring force. Okay, we have two springs here. So, this one is going to have a virtual displacement, okay, the X. This is this spring force acting that way, and we are going to have a virtual displacement, the X as well. Okay, and this will have a virtual displacement, the Y. All right. Now the linkages they are given. The length is given. Okay, 300 mm. Why this distance? Let's call this place D. Call here C. So this distance between C and D is given also as 300, and the weight is acting through the middle here. Between D and the top here is 100, and also between here C and the bottom is 100. All right. So if we and theta is given as 30 degree. So if we consider the 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 weight of the block, we can get the position coordinate as let's call it y to be equal to let's call it to be equal to okay equal to y0, sorry, y surface 0 plus 0.1. Okay, okay. So y0, y surface 0 is going to give us 0.3, because from this length of the linkage is 0.3 meters from 300 millimeters. Okay, converting into meters. Okay, so sine theta, 0.3 sine theta. Okay, now to get complete the vertical distance, we need to add the 0.1, the remaining 0.1 to it. So we have this. Okay, so that's that for that. So we can just differentiate this, differentiate y with respect to theta, and just make the theta, the y, the solid of the formula. We are going to have this to be 0.3 sine theta sine theta. Okay, the theta. Remember that we differentiated. So we have that. Now we can also consider the springs. Sorry, please, when we differentiate, it becomes cos. Let's change this to cos. This is cos, not sine. Cos. Fine. So let's go to the other ones. Now for the springs, we are going to have the spring. We know that the spring force is equal to the stiffness times the displacement. All right, and we can get x to be equal to using the information given in the diagram again, it's going to give us 0.3 again, converting 300 mm to meters. Okay, 0.3 cos theta. And of course, we will just add that small distance that was given in the question to be 50 mm, all right, between this point and here. Okay, so if we add it, we are going to have it to be 0.05, okay, in meters. All right, so we can just differentiate x with respect to theta and just make the x the subject of the formula. We will have it to be minus 0.3 sine theta, okay, sine theta d theta. So having done this, we can also go ahead and just, of course, we can just get something. For the spring, actually, we are given the compression, so we can just calculate the spring force, okay? So it's given to us as, of course, we're given K to be 3,000 kilonewton per meter. So it's simple, sorry, 3 kilonewton per meter, which is same as 3,000 Newton per meter multiplied by the 100 compression. You have that same, which is something at 0.1 meters. So you are going to arrive at 300 Newton as a spring, the spring force. All right. So having gotten that, we can now just apply the virtual work equation we talked about, so that we know that the virtual work, the U, is equal to 0. Okay, so that to apply the all the information, okay, into here. For example, considering the spring in the first instant, okay, we are going to have it to be minus 2, okay, times the stiffness, which is 300. Sorry, the force times yes, the force. Remember that we will multiply the stiffness times the compression of 100 to give us 300, okay, then times the virtual displacement, which we got to be minus 0.3 sine theta, okay. So that's that for the spring, okay, and the theta, and the theta. All right, so that's that for the spring. Remember the springs, they are two, that's why we're having that two there. Okay, so we can also consider the weight of the block. So from the mass, which is 25 kilogram times 9.81, you can get the weight, right? Times 0.3 cos theta, which is the 0.3 cos theta d theta, cos theta d theta, okay? Then minus 2m. Okay, remember for this one, 0.3 cos theta d theta, here is the this we got for the block, okay, which is the y for the block, okay. So why this is for the moment. So we're going to have this theta. So we can now solve this out. You can see that the theta is common to all the is common to the parts, so we can just bring it out. to bring it out, and we are going to arrive at 180. Okay, 180 sine theta. Okay, 180 sine theta minus 73.58, 3.58 cos theta. All right, so it's equal to 0. Now the theta is not equal to 0. Okay, it's not equal to 0, but theta is given as 30 degrees. So plugging in all the values, you're going to arrive at m to be equal to 13 point. Plug in the values and solve. Okay, have it to be 13.14 Newton meters. So this is the magnitude of the moment. Okay,